So let's talk about this ionization energy. It's an important topic, so I wanted to spend a little bit of extra time on it. This picture I'm showing you right now is an excellent way to visualize it because the bigger bar means more ionization energy. So you can see that it is hardest to take an electron from helium and easiest to take one from francium. And you can see an overall progression, though there are a few dips. And we can talk about where those changes are. But first, let's talk about the differences in first and second and third ionization energies for some elements. Let's talk about sodium as an example. You can see that its first ionization energy, 119, is pretty low. And then it gets a lot larger, and then even larger, and largest. And if you look at the Bohr model, as an example, it will make complete sense why this is so. So when you take away one electron, it's that electron in the outermost shell. Sodium wanted to get rid of it anyways. Now it has a full outer shell, and it's going to cling a lot tighter to those. So as you remove them, the ZF is going to get higher and higher as your ratio of protons to electrons changes. So it's going to cling harder and harder. And also, they're closer to the nucleus. So that second ring, after we got rid of the first electron, that second ring is much closer to the nucleus. And you can see this same pattern in magnesium and aluminum, which each have respectively one more proton. You can tell by the ionization energy how many valence electrons it has. Because magnesium's first two ionization energy are low, and then it jumps. It must have 2 valence electrons. Sodium has 1, and aluminum has 3. Now let's look at the trend overall. There are a few irregularities I just want to point out. And these are easiest to figure out if you consider orbital configurations and electron configurations for them. When you go from 2A, the alkaline earth metals, where it starts right there with beryllium, over here to boron, you can see it goes down a little bit. And that's because, remember, those first 2 electrons are paired. This is asking about removing electrons from an s orbital. You also notice another drop here, most significant in the second period, but you can see it gets less here. So the decrease in the amount of ionization energy from nitrogen to oxygen. If we think about it, we're talking about p electrons, and nitrogen has the 2 in the s orbital, and then it has 3 in the p orbitals, and because of Hund's rule, they'll spread out. Oxygen has our s orbital, and then 2 paired and 1 unpaired. Due to the repulsion of the similar charges, oxygen's not too upset about losing that electron, because then all of its electrons become unpaired. And then it gets harder again because of ZF and all the other reasons. So we can look at those trends overall. If we look at a graph, you can see highest ionization energy is helium, and then this down here is lithium, and then that is beryllium. And then boron gets easier, right? Because this is the completed s orbital, as opposed to this one, which is the 1 electron in the p orbital. And then it gets higher and higher. Noble gases never want to give up electrons because they are happy. They have a full set. And you can see this drop right here is where they start pairing up electrons in that p orbital. And you can see it in each one. So each spike will have 2 extra spikes in it. This one here, caused by going from s to p, and this one here, caused by starting to pair up electrons in that p orbital. And then you can see that carried all the way through. Now, you see there are some d electrons, so it gets a little bit more sketchy there, but you can still see the pattern overall.